The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, then let's start with problems, and as we find concept issues, we'll get to concept issues. So we talked about shortest paths, but we talked about shortest paths in a very odd way, right? I'm a coder, so for me, I'm used to, all right, I go to one of these lectures, I hear a problem, then I get out of the lecture with an algorithm and a running time, right? This time we got out of the lecture with no algorithm and no running time. So what's the point? The point is that we learned some analysis tricks that we can use for any shortest path algorithm. And the advantage of knowing that, by the way, it's really easy to forget, at least until you see the first real algorithms. If you know that, if you have to modify an algorithm, you can still use the same analysis to prove that your new algorithm is going to be correct and that it's going to be fast. So they're really nice tools to have, especially if you have to do that on a problem set or on an interview, or who knows, maybe even on a quiz. So we'll see if that happens or not. So we didn't talk about any shortest path algorithms. So we're not going to assume shortest path algorithms. Instead, we're going to use them as if we had them. No, wait, I don't like that. That's kind of annoying. Let's not do that. Let's do something else. We didn't talk about the shortest path algorithm in lecture. Let's build one right now. How about that? Let's start with a graph. Vertices and edges, right? Let's see if I can make this work. A, B, C, D. OK, so suppose we have a graph. We have V vertices, E edges, and all the edges have a weight that's non-negative. Sorry, let's make it positive, just to make things easy. It's smaller than W, so it's not too big. And they're all integers. Go.
There's brute force.
There's brute force, OK. So brute force would mean what? Enumerate all the paths? OK. Let's go for something a little bit better. Does anyone remember the algorithm that was taught in class? The structure? No. So class mentioned Dijkstra and mentioned Bellman-Ford. Let's write them up here. Bellman-Ford. And it gave us the running times, which we'll try to remember in a bit. But we don't know the algorithms. So no Dijkstra, no Bellman-Ford for us. What do we know? Let's start with a simpler case. What if there were no weights here? What if the graph looked like this? You're making my life hard. Like this. No cost. All the edges have the same cost. What would we do to solve the problem? Say we want the shortest path from A to E. BFS. How's everyone feeling about BFS? So what does BFS do, really quick? How do you run BFS?
Take a starting node, and then you search all of its neighbors.
OK, so take a starting node. Then look at its neighbors.
And then you iterate through each of its neighbors to find its neighbors, and so forth.
Sounds an awful lot like DFS. What's the difference between them?
Well, you go through all of A's neighbors before you start going through any of it. I mean, you go through all of A's neighbors before you take a neighbor and go through all of its neighbors.
OK, that's the difference.
Yeah.
And it makes a huge difference, as we've seen in topological sorting last time. So we have a list. And we're going to use it to keep track of the nodes that we need to visit. We start with A. We enumerate all of A's neighbors. And the ones that haven't been seen get stuck at the end of the list. A, B, C. A is out of the list. Then we take out the first node from the list, B in this case. We enumerate all its neighbors, A, C, D, E. Out of all these, we take the neighbors that we haven't seen, and we put them at the end of the list. Took out B. We take out C, we look at all its neighbors, we've seen them. We take out D, we look at all its neighbors, we've seen them. We take out T, we look at all its neighbors, we've seen them. So this is BFS. BFS has this concept of levels. And another way to look at levels is if you start at A and you draw a circus of radius 1, it's going to have all the nodes that are at distance 1 from A, right? Exactly one edge. Then you draw a circus of radius 2, and you get all the nodes that you can reach in 2 edges. And BFS calls these circles levels. So A is at level 0, this is level 1, this is level 2. And if you look at this list and you write down the levels, you have 0, 1, 1, 2, 2. If you add another node out here, say F, this would be discovered when we get to D. So it would go all the way here at the end, and this is level 3. So in BFS, the levels are always increasing. So if you keep track of parent pointers, the parent pointer of a node at some level will always point to a node at the previous level. So in BFS, we get the shortest path in terms of edge count. Make sense? This is recall, right? It's new, not new stuff. Everyone happy with it? So if we wouldn't have costs, we could use BFS to compute shortest paths. But we have costs. How do we deal with that? Intuitively, I'd like to make BFS go across this edge faster than it would go across this edge. Right? If I could do that, if this guy could get stuck in the queue before this guy, I would be happy. So intuitively, that's what I'd like to do. How do we do that?
Sort before adding.
Sort.
Sort your neighbors' weights.
Sort? OK. So
What if you kept track of it in a min heap? Kept track of your queue as a priority queue.
congratulations, you deserve a Turing Award. You have discovered Dijkstra. OK, let's go for something simpler. So what you just said is Dijkstra. We'll talk about it in lecture on Tuesday. Very good.
I could have an adjacency list, and I think using what you said, just sort it. So by cost. I mean, weight.
OK, so let's see how this would work. So we have A, and we're pulling A out of the list. And we see its neighbors are C and B, right? The distance to C is 2, the distance to B is 4. So we start with A. So does this mean that I'm going to put in B before C? And then, so I'm going to put in C and then B?
Oh, I mean, it doesn't really matter. You just at the end you just sort, or I guess you could add the costs, like associate the costs of B with 4 and C with 2 within your adjacency list.
OK, so that's how we would keep track of costs,
Yeah,
right?
so like
One way.
For the key would be A, and then the value would be like a tuple of B and its cost, and a tuple of C and its cost.
OK, so you're saying that what I would have in this list is B with a cost of 4 and C with a cost of 2, presumably in the other way around, right? C goes first. Like this. And then I take out C, I explore the neighbors, so on and so forth. The moment I did this, I already lost the battle. Because see this path, ACB, length 3. If I put both of them in the queue, then the parent pointers are going to look like this. So I already have a bad path from B to A.
Okay, well, don't add that note then.
OK, then how do we do it?
I guess, well, you can talk to each of them and see which one's lower, and then only add that one if it's the lowest, and then you keep
Well, you two need to talk together because you're getting to Dijkstra too. You're both going to rediscover Dijkstra. So that's great, but I'm looking for something simple. So this is too complicated. If you're going to do Dijkstra now, then what are we going to do on lecture on Tuesday?
More extra problems?
Well, I think Srini wants to talk about Dijkstra, so let's not get there.
How do you do this without doing Dijkstra?
Good. That's exactly what I want to know. So let me give you another hint. So the first hint was that I want to go through this edge faster than I would go through this edge. The other hint is that we're allowed to change the graph.
So, I mean, for each node, I mean, is this what we were talking about in lecture, or are you thinking of something else?
What he might have talked about that at the end of lecture.
I mean, where you're putting the current weight for each node inside the circles.
No.
Oh, okay.
You could add it, and then just if you find a better path to B, if you're always relative to A, then you could just delete that path from B to 4. So at the beginning, add them all, but then.
You're risking to have exponential running time. Those are all valid optimizations under some constraints. Like this one's good if you're willing, if you don't have too much memory, but the time goes up. So I want my graph to have edges with no costs. As if I have costs, this is not going to work. BFS is not going to work. We can't tweak it. If we could tweak it, then that would be another Turing award.
So like create dummy nodes?
Create dummy nodes. How do I do that?
Put a random node in between A and C.
Okay. Why am I doing this? So now I have two edges, and they have cost.
1. Then you put 3 nodes in between A and B.
Okay.
Or, yeah, 3.
And now here I have 4 edges, right? Ah, oops. 1, 1, 1, 1. There was a 4 here before, and there was a 2 here before. Do you guys see what's happening? So instead of one edge of cost C, I have C edges. So now BFS is going to take C steps to go through that edge. And all the edges now have the same cost. So this looks like a problem that BFS can solve. We know it can solve. We prove that it can solve it. Well, CLRs did. We take their word for granted, sort of. So this works, right? Is everyone happy with it? Does it make sense?
So basically, we get to B before you ever get to, through C before you'll get to B on the other path.
Yep, so this is a path of length 3. So this node is going to get in the queue first, then this node, then these 2 nodes. And they're going to get in the queue from C. So let's see what happened here. So this is really important because this is what you're going to be doing in real life. Chances of having to build a new algorithm, kind of slim. Why don't you want to do that? So you take Dijkstra and you tweak it a little bit. If you did that, you have to go through the analysis and prove the running time again, prove the correctness again. Time-consuming, error-prone. It's really hard. However, what happened here is that we have some problem that we want to solve. Say we have the raw input for that problem that we're trying to solve. That is this graph that I drew on the board. And we apply some transform. And we get an input that's suitable for an algorithm that we already know. And I'm going to take a shortcut here because I don't. So we applied a transform, right? We took this graph and we built a new graph in. And this is hopefully easy, right? Take an edge and split it up, put in fake nodes. This is easy. We know how to code that. And now we have this algorithm that we already know, and we're treating it like a black box. We know it's correct. We know it's running time. We're not questioning them. We're taking them straight from the textbook. They have to be right. By the way, what's the running time of BFS? And sorry? Very good. I can hear you very well. So then BFS is going to give us a path, right? And the path is going to look like this. It's going to be A, fake node, C, D, fake node, E. If you give this back to the guy who gave you the problem, they're going to be like, what are these fake nodes? I don't know anything about them. This doesn't make sense. So you need to take this raw output, and you need to transform it again. Based on what you did on this transformation, you have to read out the output. You have to interpret it. So this is either interpret or read out. And then you get a nice output. That's the output to your original problem. This process here is the most likely way in which you'll use your 6006 knowledge. And this is replaced by any algorithm that we taught. This is replaced by any real-life problem that you'll encounter. OK. So there's one missing step here. We know the running time for this. Let's find out the running time for the whole thing. So in order to do that, we have to figure out, given this original graph, let's say that now in the original graph we have V prime vertices, E prime edges, and W prime weights. We have to convert this into V plus E. So we have to see when we make this transform, how many vertices do we get, how many edges do we get in terms of the original graph, so that we can compute the running time. So in the original graph, V prime vertices, E prime edges, W prime weights. In this new graph, how many edges do I have at most?
Like a
Proportional to the weight.
yeah.
So U, E,
Sorry?
so times E.
Yep, perfect. So each edge has cost at most W. So that means we're going to split it up into at most W edges. How many vertices are we going to have? W prime, E prime,
Plus B prime.
plus V prime. Don't forget about the original ones. They're still there. OK, so total running time for BFS on this new graph is? OK, I'll put it the other way around. Plus W prime, E prime. OK, so this is the running time that we have. Now, does anyone remember Dijkstra's running time and Bellman-Ford's running time?
Was it proportional to weight?
So what's the running time for Dijkstra?
V log V plus E.
Almost.
V log V.
Oh, wait. Oh, yeah, I think you're right. V log V plus. Are you reading this from CLRS? Or is this what we got?
That's what they even
Okay.
mentioned.
They've given them.
You need to use a fancy heap to get this running time. Yeah. You can get this, but you need a really fancy data structure for it. In real life, the running time looks more like E log V. OK, and how about Bellman-Ford?
V times.
OK, so let's take this running time for Dijkstra, because this is what you're going to implement in real life. And we can argue about that after next lecture. For now, take my word for it. And let's compare it to what we got here. V is smaller than E in most sane cases. So let's say that this is actually W prime E prime. So if you compare this with this, you'll see that if W is smaller than log V, well, smaller or equal, then this algorithm is not worse than Dijkstra. It's on par with Dijkstra. So for graphs with small costs, we discovered an algorithm that solves shortest paths. We walked in this recitation knowing no algorithm to solve shortest paths. Now we have an algorithm, already in a much better position, right? And we didn't invent anything new. We don't have to prove correctness. All we did was one of these transformations. OK, how's everyone feeling? Do things make sense? Everyone happy? Okay, let's talk about another problem that also uses this structure. So suppose we have the same graph that we had before, or actually any graph with v vertices, e edges. Now we know how to compute shortest path. So we can assume these as black boxes. So we're going to use these as they are. So we have a graph with v vertices and e edges. A, B, C, D, E. And let me copy the costs really quickly. 4, 2, 1, 2, 1. So suppose this is a highway system, right, like in Google Maps. And we have two brothers. They start off from a place, and they have to end up in another place. They're going to drive together. They want this to be sort of fair. So every time they go between two cities, they're going to switch seats so that none of them drives too much. So say the brothers are Tim and Jim. The names are wrong. This is actually a problem from last year's quiz. So by the way, real problem. You can pay attention now. So these are two brothers. They're going to alternate, right? One of them is going to drive across one road, then the other one, then the first one, then the second one, so on and so forth. Now, Tim has a much better sense of direction than Jim. That's just how things are. And if you ever driven long distances, the hardest thing to do is to get from the city to the highway. So like if you have to drive from here to New York, hardest thing to do, get out of Boston and onto the highway. Then at the end, hardest thing to do, get from the highway into where you want to go through New York traffic. Everything else, piece of cake. So we want Tim to handle both of these situations. So the driving path must start with Tim and must end with Tim. Otherwise, God knows, they're going to crash. So first off, let's convert this into graph terms. And then let's solve it.
It's already in a graph.
Well, so I have this constraint that they're going to switch seats and that Tim has to start and Tim has to end. How do I phrase this in mathy terms, in graph terms?
We're starting at where and ending where?
We're given where in the graph. So we're starting at S, ending at T, some points in the graph.
And people have to drive an entire edge, is that true?
Yeah.
Okay, so then, so basically, yeah, Jim has to, whoever the good driver has to drive on the edge that's adjacent to E and S.
Yep. Okay.
You basically need like an odd number of edges.
Yep. So I want the shortest path with an odd number of edges. Why odd number of edges? If we look at the edges, Tim's going to take the first one, then Jim, then Tim, then Jim, then Tim, then Jim, and no matter how many I have here, it has to end with Tim. So I'm going to have an odd number of letters here, therefore odd number of edges. Right? So I want the shortest path that has an odd number of edges. And as the hint, we're going to use that trick over there. So, yes?
But the shortest path isn't necessarily like the fairest, right? Like in terms of distributing driving.
One of them is going to drive one more road, such as life. Oh, sorry, one more edge segment. So Tim's going to drive, say, Tim's going to drive 3 times, Jim is going to drive 2 times.
Right, but like in terms of the weights.
Oh, yeah, we don't care about that.
Oh.
Jim doesn't know where he's going anyways.
It's a
Okay.
minimum, you have to have a link-free path, right? Because you don't just want Tim to get out to the highway and be like, oh look, our journey's not that far, and then
So I want the shortest, so I want the path with the smallest cost.
okay.
So smallest total weight.
But I mean, like, in theory, it could be length 2, right? 'Cause
Well, if it's length 2, then it's not going to be good because they're going to crash.
well, no, like Tim would Oh, I see. They have to switch every time.
Yep.
Okay.
Tim can't drive for 2 consecutive edges.
Okay. I mean, you could use breadth first search and once you get to the end point, eliminate all paths that are, you know, an even length, and then of those paths, go through them to see if which one's the lowest cost.
So you're thinking enumerate all paths of even length? No, just to make sure I got it.
Yeah.
So this is cool because it lets me show something else that's cool. So enumerate all paths of even length. Something else I heard, enumerate all the shortest paths. For both of these, let's look at this graph. ST, all the paths have length 1. How many ways are there to get from S to T?
A lot.
2 to the 3. 2 ways to go across this diamond, 2 ways to go across this one, 2 ways to go across this one. Right? 2 times 2 times 2, 8. If I add another diamond, how many paths? 1 more? Okay. So the number of even paths, or the number of shortest paths, the number of whatever paths I can think about is order of, come on guys, math. Go.
2 to the number of diamonds.
Okay, which is
And 'cause it's just
roughly 2 to the vertices, right? Exponential in the number of vertices. Not very good. Not very good. We can't do this. So it's better that we talked about it here than you try to do it on the quiz and you have to discover this on your own, right? So good comment.
I didn't understand what he meant by that in lecture, so that makes sense.
That's completely different. That's another,
The thing he was talking about?
that's different.
That wasn't, okay.
Yeah, that's where relaxation can go wrong. So he showed that if you relax the edges in a random order, you can have an exponential number of steps. This shows that there are an exponential number of paths for any graph, no matter how good your algorithm is. Okay, so we're not going to be able to enumerate them. Let's try something else.
Any other suggestion?
Uh,
Just look at all those
yeah,
those paths?
so you're doing this, right? You're looking here. Everyone's looking here. How about this?
You should do that.
There's that, right? There's a transform. You need to transform your graph in some way and then run the algorithm. And then reading off the output should be easy. I claim that the hard step is the transform step, not the read off step. Okay, so let me give you one more piece of intuition. So we're going to keep track of state somehow. So remember Rubik's Cube? We had one vertex for each state, right? A state represented a configuration of the cube. Here, suppose I got I'm looking at a path from S to D. The problem that I have with this is that if I have an algorithm that tells me the shortest path from S to D is something, I don't know if it's even or if it's odd. It's not keeping track of that. So it's missing some state. The state that it's missing is whether the path that I used to get here is even or odd length. So I should do something to the graph to keep track of the state.
So can you BFS it once to find? So like, right, because if you BFS once, then you know that B and C are all like 1 away, and then you know that E and D are 2 away.
Well, B might be 2 away if I take this path. So it might be 1 away, it might be 2 away. But this is good. So this is what you'll do on a quiz, right? You come up with an idea, and then you're going to think about it for a bit. If you get stuck, try to convince yourself that it's wrong, or just if things get too hard, discard and look somewhere else. So this is thought process, right? You think of something, backtrack, 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 and eventually you get to the right solution. So let's go over the solution for this one, and then I'll give you a hard one that is sort of like this, and then I'll want the solution from you for that one. So I'm going to draw this graph in a bigger version, so I'll have to erase this. So this is a cool concept. You will be able to do a lot of things with it.
Wait, is this problem solvable by Dijkstra?
Yeah.
Okay, just curious.
Yeah, we'll run Dijkstra on it after we transform it. These are big nodes, right? Why am I doing it this way?
Is that like Seattle, Portland, San Francisco?
Well, it's because I'm going to need room for copies. I'm going to make a copy of each node to keep track of state. So instead of one node, I'll have two nodes for each node. And I have two nodes because this is what lets me keep track of state, odd path or even path. Let me erase the edges because that's not how it's going to work, actually. So instead of having a node A, I'm going to have a node A even, and I'm going to have a copy A odd. B even, I'm going to have a copy B odd. C even, copy it to C odd. D even, make a copy to D odd. Oh, wait, this is E. Sorry. Sorry, my bad. OK, so suppose I got to A using an even length path. If I take the edge from A to B, I will get to B using an even length path or an odd length path. So if I get to A using an even length path, then from there I'll get to B using an odd length path. Sorry, 4. Using this exact road. That's a nice way to name it. I've heard worse. So if I get to A using an odd number of edges, how many edges will I have when I get to B? OK. So this edge became these edges here. OK, now let's do the edge between B and E. I get to B using an even number of edges. I take B. Do I get to E even or to E odd?
Odd.
OK. I get to B using an odd path. What are the lengths of these paths?
5.
OK. Cool. God, this is starting to look ugly, you're right. Let's do AC and stop there. A even is connected to
Odd.
C odd by a path of length.
2.
And A odd is connected to C even by a path of length. OK. Is this starting to make sense?
I mean, you just.
So all the edges are going to look like this.
So are those like two independent graphs?
I have edges connecting them. But I like your question. So the reason this is ugly is because I'm looking at a 2D projection of a 3D graph. If I had a holographic display, which would be a lot nicer, then I would do something along these lines. I would say, 2 pieces of paper. I would draw the graph. I would draw the original graph and call it the even graph, put it here. I would draw the graph again, call it the odd graph, and put it here. So this is my 2D graph. This is my map, the original map. And this is state. The third dimension is state. So when I start, when I'm at a node and I use an even number of edges to get here, I'm going to go take one edge and go to another node using an odd number of edges. So all the edges are going to go from here to here and from here to here. Does it make more sense now? So the reason that looks ugly is because you're seeing the graph like this. If you could see it like this, and maybe play with it a little bit, it would make more sense. It wouldn't look as ugly. So there are two graphs, the even graph and the odd graph, and the edges between them represent you doing something. So when you transition, when you take a highway, you transition from an even state to an odd state, and from an odd state to an even state. So that's why the edges are the way they are. OK, so now let me see if you guys get it. What node do I start from? What node do I want to end up in?
A, when you're ending up at E, it's for S and TR.
A even is C odd, or E odd.
OK.
Oh, there's two odds.
Yeah.
Expanded BFS.
OK, so I heard three answers. One of them's correct. Do you want to vote, or do you guys want to figure it out? Talk it out. Fight. OK. We start from A even, and we end up at E odd. Why do I start at A even?
We've seen exactly 0 cities when we started A.
Yep, so the original path has length 0, which happens to be even. And we want to end up with an odd length path. So if we go from here to here, see how because we have two nodes instead of each original node, the path is going to alternate between even and odd. And it's going to keep track of the state that I didn't have before, and it's going to just do the right thing. It's magic. It works. So let's see what's the running time of this new algorithm. How many, say my original graph had V and E. How many new vertices do I have?
2 times
How many edges?
20.
Each edge is copied exactly twice. Which algorithm am I going to use? All my weights are positive because they're the time it takes to drive somewhere, or the distance or something. So which algorithm do I use?
We can't use facts for the, or can we?
That.
You can't use breadth first search because you have weights.
Oh.
So breadth first search is not going to find the right answer.
Well, if we
Oh,
split it up.
you want to use this thing.
Yeah.
Well, so we don't have to worry about that because now we put the shortest path algorithm in a black box and we have them.
Oh, so we can use them now.
Yeah,
Okay.
so we use these black boxes. But what we need to know is when do you use this black box and when you use this black box. Which box is faster, by the way? Please give me the right answer.
Extra?
All right, Dijkstra is faster. So whenever we can use Dijkstra, we will use Dijkstra. When can't we use Dijkstra?
When it's negative cycles.
Negative,
Wait.
negative weights. So if I have weights greater or equal to 0, I'm happy I can use Dijkstra. If I have weights that are smaller than 0, well, whatever. It's going to be slower, but I can still solve it.
It's like arbitrary negative weights.
Yep. Arbitrary negative weights. So all the edges here are positive, so I'm going to use Dijkstra. Very good. So the running time will be order of V log V plus E. If you're a theory person, if you're in real life, it's E log V. So hey, this is exactly the running time for the original graph. So the transformation only increased the graph size by a constant factor, so same running time. Pretty good, right? OK, let's do one more problem. Let's do the hard problem now. Are you guys getting ready for the hard problem?
Let's do it.
Just wanted this even
I
odd
didn't
thing.
really see the problem, but it's okay.
If we hadn't seen this, we probably wouldn't have thought of it.
Yeah,
in
like
any.
how would we think about this?
Well, that's why we taught you this.
Okay.
Like,
So I wanted to do two things. I wanted to show you that trick, which is a cool trick. Keep track of state by doubling or by multiplying the vertices that you have. And I wanted to go through some wrong solutions and figure out why they're wrong so you can develop an intuition. Because when you're going to get a new problem, you're going to think of something. Unless you're really good, unless you're destined to win a Turing Award of some sort, the first solution will probably be wrong. Even if you're destined to win a Turing Award, the first thing that comes to mind will probably be wrong. I'm willing to bet Dijkstra didn't think of Dijkstra off the top of his head when he heard about the problem. So what you want to do is get an intuition. So when you think of a solution and it starts getting complicated or things start looking wrong, you want to back out and think of something else. The more things you can consider, higher chances that you're going to stumble upon the correct solution. So that's why we're building an intuition for bad solutions. I'm not just saying, hey, give me a solution and now I'll tell you it's wrong. It's not just to embarrass you or something. There's that intuition building step that's really important. Okay, so there's this network that we keep talking about. There's this highway network, except this time it's a bit more complicated. So for each edge, I have two things. I have a fuel cost, which is constant. So a fuel cost is a function of the length of the road. But now I have these realistic highways where I have traffic. If you try to go from Boston to New York, 2 a.m., 3 hours. Rush hour, 6 hours. So we have to keep track of this in some way. Well, we're going to split up the day into minutes. Say you have m minutes in a day. Can anyone tell me what m is really quickly? Not a number, a formula, something.
What's 3,600 times 24? Right? Oh, no, that's seconds.
52 seconds.
Okay.
Whoops. Divided by 60.
All right. So this is how many minutes in a day? So this is how many minutes we have in a day, right? Okay, so we're going, for each edge, we're going to have a function that's the time cost of the edge. So it's the time cost of this edge. And it's going to say, if I start at a certain time, it's going to take this many minutes to go across the edge. So for each street, I know how much time it's, each highway, I know how much time it's going to take to go across it, given when I start. And I know how much fuel I'm going to consume. By the way, edges are directed now, just to make our life easy. So this graph is going to be like this. Let's see if I can get this right.
It's actually like Boston, where they've got one-ways everywhere.
Well, so the real reason I'm having this is the time to go across the street might be different, across the highway might be different depending which way you go.
Oh, so you have
Getting
to go
into
to
Boston in the morning versus getting into Boston in the evening, which one's easier? Sorry, versus getting out of Boston in the morning.
I would drive, so.
Intuitively, I'd say it's probably harder to get in the morning because people are going to work.
Okay.
And it's easier to get out. But yeah, I don't know either.
No, the 95 calls are brutal.
Okay, we have an answer. Okay, so our edges are going to be oriented. And I want a road that, so I want a final itinerary that gives me, that satisfies two constraints.
It would have to be D, not E. We'll get 2 copies of it.
Yeah, that's not good, right? Okay. New York and New York. So so I want to see how fast I can get to my destination. That's my top priority. If I can get to New York at 5 p.m., I want to get there at 5 p.m. But if I have I don't want to get there at 5:01, for example. But if I have 3 ways to get there at 5 p.m., I want to choose the way that's the most eco-friendly, so least amount of fuel. So out of all possible ways, the fastest way. Out of all possible fastest ways, the way that consumes the least fuel. Go. You have 2 minutes.
Nice.
Maybe 5.
And we have the same costs for the.
So each edge always has the same fuel cost.
Oh, no.
But depending on when you start going across it, it's going to take a different time to.
But we don't know what those times are.
They're going to be different for each edge.
One guess, take Dijkstra, find the shortest path length, and look for all path lengths that are that length. I don't know.
So we have the issue that I might still have it. Oh no, never mind. Sorry, I erased it, so it's not on your mind anymore. We have those diamonds that show you that there might be an exponential number of paths with the same length or the same distance.
And it doesn't help that we know we should cut off it.
Nope.
Yeah. Right.
So we need to do the process that I just erased. So transform the graph in.
Right.
So the thing is now you're missing state, right? This misses state. This tells you how many edges you have to get from source to destination. But we're not keeping track of some state that is vital. So transform the graph to keep track of state, run, say, Dijkstra, and then interpret the output. So what state do we need? Let's think of that.
Fuel cost, I think.
Sorry?
The fuel cost is
Like-
the same for each edge.
Mm,
It's just the time is different depending on traffic.
but like, don't we want to keep, because like once we have found the fastest path, then we want to like see like according to our fuel cost, right? Like,
Yep.
which one do we want to take? So won't we like, so like thinking about the priority, our priority is time.
Yep.
So we want to like save fuel, I feel like, as a state to check it.
So the problem is I don't even know if fuel costs are integers. I can't keep fuel as a state. So how many copies would I have? For each vertex, how many copies would I have if fuel is a state? Who knows? So let's try something else. But you're on the right track. Let's take a variable and make it state.
So for every vertex, can you keep track of what's the shortest time it took to get there?
What's the shortest time it took to get there? So how would you keep track of that? Would you make that state, or how would you keep track of that? I'm not disagreeing. I'm trying to understand your...
So like for example, like let's say if you have B, right? Like
Okay.
let's say at vertex B, let's say it takes like 1 hour to go from A to B, and so when you
So it depends when you start, by the way. So
Right.
how much time it takes depends on when you start. So like if you start at 8 a.m., it might be an hour. If you start at 9 a.m., it might be 2 hours.
Right.
Do you need to have a finite number of states?
It's nice if it's not infinite, but it doesn't have to be constant like we had before. It can be more than constant, for sure. So what are you thinking?
I want to use time as a state.
I like that idea. Let's try to do it. So we're going to use time as a state. How many vertices am I going to have for each vertex? So for each original vertex, how many vertices am I going to have in my new graph?
3, 4, 4, 0.
I feel like it grows exponentially.
Well,
Well,
that number.
The sum of all times.
Yeah.
So if I say, hey, I'm at this vertex at this time, then I'm going to have m vertices for each original vertex, right?
Right.
So I promise that the resolution of time is minutes. So I promise that this thing gives you an integer number of minutes.
Can it be like in the days though?
Suppose we can get from source to destination in 1 day. So let's see how it builds this graph first, and then we can figure out the rest of the things. So for each node, I'm going to make m copies of it. So suppose in my original graph I had a node. I'm going to have m copies of that node, and each copy has the original vertex and the time when I'm there. Right? So there are v of these, and there are m of these. Yes?
Totally makes sense. It's a great idea.
Yeah, you had it. Great idea. So far, so good.
And then
So-
you connect it to the appropriate next one.
Yeah, so let's see how we do that. Let's do that. So suppose we have an edge from U to V, and yeah, how are we going to connect this? How are we going to transform this? How many edges are we going to make from that edge?
So you should only make, oh my goodness. Do you have to do it from every start time, I guess?
Yeah.
Yeah.
So you'd make
So-
m edges.
Okay. M edges. So from U and a start time to V and what?
T plus TC of T.
T plus TC of going through that edge, right?
Right.
TC of going from U to V at this time.
Right.
Yeah, like this. So you start from a time. So the edge points from the time that you start up until the time when you'd be able to finish. So up until the time where you'd be off the highway and done in the next city. And we need one more type of edges. There's one more tiny trick. So if I'm somewhere in Massachusetts and I know that it's really bad now, I might prefer to wait out for a few minutes, go to a bar, and then come and drive. Okay, not to a bar, go to a food place and then drive later. So
vertical edges that
represent waiting. So
that have 1 minute between them.
okay, so how do I do that?
So from you to you
Okay,
with a cost of 1.
from you to you. Well, so from you
At time
and at time t
plus 1.
to you at time t plus 1. Okay, I like this better. And what's the
From you.
fuel cost of this?
0.
Okay, so here if this edge had fuel cost fc, then the new edge is going to have fuel cost for the ones on the top.
Is it proportional to minutes, speed?
It's the same.
Just FC.
So fc stays the same no matter when we go through the highway. fc is a function of the distance of the road. So this edge becomes m edges with the same cost, and then I have to have vertical weighting edges. So if we had the holographic display that I talked about earlier, you'd have m sheets of paper this time. You start at time 0 at your source, and then your edges represent the moves that you could make. So you could start in Boston at 8 a.m., and you could take I-90 and end up in, I don't know Massachusetts city names, Albuquerque at 9 a.m.? Okay, I don't know, sorry. I don't know. Amherst, okay. So you start at Boston 8 a.m., you end up at Amherst at, 9, 10 a.m. Right, so this is one edge. So the edges represent the moves that you could make in this graph. Does this make sense?
Wait, I understand the 2 last lines there. What was the, I don't really get what we were doing there. I need to.
Okay, so let's see what we're trying to do here. So we're saying that if I'm a node U and I'm starting at time t.
Yeah, so it's like one paper.
Yep.
Okay.
So this is, I'm going to go on a road, right? I'm going to go on the road from U to V. So where am I going to arrive?
There would be at some time. Plus
Right.
that.
So
Okay.
now we have to figure out what time we're going to arrive at. So the time that we arrive at is the original time plus whatever time I'm going to spend on the road. What's the time I spend on the road? It's not constant because I have that timetable that includes traffic.
Yeah.
So this is what this tells me. This is what this big ugly formula is all about. It says the timetable for this edge, assuming you start at time t.
Oh, yeah.
That's all there is, nothing else.
What's the second line then?
So the second line is waiting. So if I don't have this, then I'm constrained in that I have to drive all the time. Right? I go from here to Amherst, then I have to go from Amherst to somewhere else and keep going, keep going, keep
Well,
going.
she's just saying you to you, so this is the pausing.
Yeah, this is where I wait for a minute.
Okay.
So if I wait for a minute, I don't consume any fuel, and I go from time t to time t plus 1.
Okay.
Does this make sense? Do we want to analyze the running time for this really quickly?
Sure.
So how many edges?
E times m.
Okay, let's do vertices because vertices is quick.
V times m.
Okay, so edges is, you're saying E times m. Almost.
Pause there.
Okay, so there's a pause, right? How many pause edges do I have?
V prime.
V.
Um,
M.
V times M, yeah.
okay, so this is how many vertices, this is how many edges. Plug this into which algorithm? Dijkstra or Bellman-Ford?
Extra. It's all positive.
Done. Yay, we solved the hard problem.
Why do you have
how
V
do you
times
ensure that the time's right? So do you have to go through and see if there's a path?
How do we read the solution? That's good. That's a good question. I like that. So we're going to have m vertices at the destination, right? Let's see how they're going to look like. First off, if you start at 8 a.m., maybe you're not going to make it to New York at 8:01 a.m. So the vertex that says New York at 8:01 a.m. is probably going to have a cost of plus infinity. So first off, the really early times are going to have a cost of plus infinity. Not going to happen. Then at some point, the cost is going to become finite. That's the fastest way you can get from Boston to New York. And in the shortest time. Using the least amount of fuel. So the cost that you have there is the answer to our problem.
So basically when you get the result, you have to iterate through all M.
All m vertices that correspond to the destination.
Right.
Okay, so what I like about this is, so the costs are going to look like this. They're going to be infinity, 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 all the way up until some point. And here you're going to have your final answer. The cost to get there the fastest. Say you can get there at 3 p.m. This is how much fuel you have to spend to get there at 3 p.m. But if you're willing to wait until 3:01 p.m., you're going to have the fastest cost you can have for that. If you're willing to wait until 3:02, you're going to have the answer for that too. So here you're going to get the whole trade-off curve of if you're willing to wait for a few minutes or if you're willing to wait for an extra hour, how much fuel you can save. So I think that's cool about your question. Okay, you had a question too.
Why did we have v times m in the e prime expression?
So first off, we have e times m, right? We're good with these. These are the weighting edges.
So we are waiting like after every minute or what?
So the weighting edges are vertex time to vertex time plus 1. How many vertices? V. How many times?
M.
Okay, so it's v times m. Because at each minute, you can be at a certain city and decide to wait 1 more minute to stay in the same city. Okay. Does this make sense? Thank you, guys. I'm really happy we solved the hard problem. That's good.